I'm going to tell you today about QGeNIe, which is a link between qualitative and quantitative Bayesian networks. And here's the brief outline. The presentation is going to be really short, and I'm planning to leave some time for looking at the software itself. In the presentation, I'm going to essentially motivate why we have developed this and what kind of things can you do with it. Bayesian networks are essentially a wonderful invention that happened around 30-something years ago. The graphical part is a representation of the causal relations among the model variables. The graphical part is fairly easy actually to construct. There are some problems with it, difficulties, but a skilled knowledge engineer should be able to draw the graph fairly quickly. They lead to enormous savings in the representation of the joint probability distribution. This model of 70 variables can be represented by the graph and on around 2000 parameters because it represents around 2400 independencies. These are the missing arcs, which are very important in achieving savings. From the very beginning, there was interest in abstracting Bayesian networks to qualitative schemes. There were two main reasons for that. First is the difficulty in obtaining numbers. So why can't we specify networks in a qualitative way? The second is the difficulty with inference, which is NP-hard worst case. So qualitative schemes can be much faster. That was the hope. The three main approaches that I'm familiar with is the kappa calculus in Bayesian networks by Goldschmidt and Pearl, enhanced by Darwish and Goldschmidt, and there were other follow-up papers. Essentially, it has Bayesian networks with conditional probability tables, but in the tables there are no numbers. There are just there are numbers, integer numbers specifying the order of magnitude of the number. And the QPNs, qualitative probabilistic networks, by Mike Wellman, I also had some contributions to them in product synergies and the algorithm for inference in QPNs with my advisor Max Hennion. There were also other people who did follow-up work. And there's also work on patterns in QPNs, essentially extending, enhancing, discussing the QPN framework in the light of what we know about various types of interactions and canonical models by Peter Lucas, also followed up by other work. Interestingly, most of this work focused on the inference, which indeed is much less complex than general Bayesian network inference. Here is an example of an algorithm for the QPNs that I co-authored with Max Hennion. Suppose you observe low oil level in your car engine, and then you would like to calculate the effect of observing blue exhaust. What happens is the arcs are labeled by the sign of influence between nodes. The sign can be positive, negative, or a question mark. This network is very neat. There are no question marks, no varying influences. Through the arcs, you propagate the sign. The problem is that because of this observation, the multiple paths to reach any of the nodes can have negative signs, opposing signs. So normally the paths have a positive sign, but intercausal inference between the causes of an observed effect have negative sign in this case. And then the effect of that is that you get a lot of question marks, which is essentially that the qualitative scheme is unable to calculate the effect of observation. And that's really very, very typical for QPNs. For any sizable network, you will get a lot of question marks when you perform inference. There are two ideas that I wanted to mention that are underlying the qualitative QGeNIe. The first is that precision of parameters does not seem to be crucial. We performed a series of experiments with my wife Agnieszka Oniszko, and what we did is we progressively rounded, made rougher parameters. These are all scatter plots. X-axis are original parameters, y-axis are rounded parameters. So you see that parameters become one of a small set of possible values. As we progressively roughened the parameters to almost an absurd roughening where every parameter was 0 or 1, actually it wasn't 0 or 1, it was epsilon and 1 minus epsilon, because as you know, zeros are very, very troublesome numbers in Bayesian inference. Once something is 0, it can never become anything else. So zeros should be avoided in models unless we are absolutely sure they are zeros. So what did we observe? Here is the model HEPAR that I showed a few slides back. We showed the diagnostic accuracy of HEPAR as a function of the roughening of the parameters. Logarithm of the number of intervals, 100 intervals, 10 intervals, 1 interval. As you see, the accuracy of HEPAR, diagnostic accuracy, is suffering a little bit from rounding, but not much. Even when you have this absurd epsilon 1 minus epsilon values for every parameter, the accuracy suffered less than 20%. And the second thing is computational complexity. It is, as I mentioned, worst case NP hard. But we have huge models that are calculating very quickly. This model, which looks like a spaghetti, can be updated in a fraction of a second. It's a practical model for the diagnosis of diesel locomotives, can be updated very quickly. And it also shows you, it looks like a spaghetti, but it's the missing arcs that matter. Even though there are 3,500 arcs, there are over 2,000 arcs missing, and that makes it an efficient, computationally and representationally efficient model. So the three things, really. Precision doesn't matter too much. Computational complexity is not a showstopper. And the third thing is that knowledge engineering is still a problem. So whatever we can do to help here, we should do. These three underlie our approach to QGeNIe, a qualitative interface to an otherwise quantitative network. So we are not worried about calculation. We can have a quantitative network, but we provide a qualitative interface to it. So QGeNIe, the building blocks, there's only one building block, the Morgan gate. It is a kind of combination of noisy OR, noisy AND, and negation. As you know from the Morgan's laws, with negation and AND, or negation and OR, you can represent any logical function. So we have a logical function that can be noisy, like a noisy OR, and that is the building block. This logical function is quite intuitive. It has four types of influences. Cause is like a regular cause in a noisy OR. The cause makes the effect more likely. Barrier makes the effect less likely, so it's a negated cause. Being alive, a requirement, is required for the effect to happen. If the requirement is false, the effect will not happen even, regardless of all the other causes. And then inhibitor is a cause that works like an AND. If it's true, then it will make the effect false. If you have flu and pneumonia, which cause fever, you may have high fever. If you take Tylenol, the fever will go down, no matter how many causes there are that make the effect likely. QGeNIe. I'll have a few minutes to show you the actual interface, but just wanted to point out a few things. It hides numbers and operates on rough order of magnitude estimates. Elicitation is just elicitation of the De Morgan gate, which requires one number per arc and one number per node. Very few parameters. The posteriors are shown by colors. You see that live. It is especially useful in complex domains in which it is hard to create exact models. So you approximate them, roughly. One number per arc, one number per node. Models like this are a great starting point to model quantification, and they've been shown extremely useful in group discussions, group decision making. These are the two applications. In the network quantification, the number of parameters you need is very small. Once you have this qualitative model and you are reasonably happy with it, you can do initial testing, refinement of the model here. You can export it to QGeNIe and then refine it further to a full quantitative model. And it's really a fairly fast process to do that. And I also mentioned this group decision-making sessions. Models that can be built really very fast can be shown on a screen, and that avoids misunderstandings, arguing in parallel to each other about different things. You have one focus that you can modify as needed, and you can ask questions of it. You get this instant gratification interface that shows you the answer to your what-if questions. The last slide is a sidestep from quantitative to qualitative modeling, definitely very useful. Let me use the last few minutes to give a short presentation of QGeNIe live. You need one number per node. That's the prior belief of the node. As you change it, the color of the node will change because that's also the marginal. You can change the color of this node. You can make it green. Oh, it's been observed. This is the prior. Of course, this has been observed to be true or false. That's why the color didn't change. Every arc has a number. There's a clear meaning of each of these numbers as you work with it. The number, the strength of the influence is also shown by the color. You see, this is more pink, so the influence is weaker. And the arcs are of different types. Now, what can you do with it? You can ask questions. What if my client comes back and says, the airplane that I should build for the client should have an increased load? You double click on this, observe true, and you see the profits change. It's false, it's darker green. Good. There is going to be profit. When it's true, it's lighter. The profit is going to suffer. Higher speed requirements make it even lighter. Leads to technical problems, but still we are in green. You can also ask questions, what can I do in order to make sure that the profits are at a reasonable level? This is essentially using cross entropy. For every node you can specify whether you can manipulate or observe it, and then this sorts them from the most to least influential on the focus of the inference. So you can make a change in it. You see that that's the biggest change on the profit. Not surprisingly, that's what it was calculated to be. Insufficient advertising is another of those strong effects. Effects of other things is less clear, less powerful. This program has been applied in military environments. The model was constructed by Brad Hayes and Jeff Sands at Naval War College. The idea here was to model stability of a region and various aspects of that stability. The model is fairly large, has 99 variables. Hidden in submodels. The colors propagate to the submodel icons, so you can see, again, green or red color. And you can also ask the questions, what can I do in order to make the stability, to impact the stability? Here are the most effective actions to impact stability. We didn't see much change, but I guess it's a complex system that where changes propagate and can impact the stability ultimately. Finally, you can have dynamic Bayesian networks that are qualitative in nature. The colors are shown as slices. You see the gradient of things happening. You can see the marginal probabilities as they change over time in the 24 time slices. You can see the effect of that. If I build a high-quality product, that's the way that company's reputation, product reputation, market share will develop. If I make bad, poor-quality product, that's the way they will develop. Aggressive advertising, if I don't advertise, is going to be even worse. If I advertise, it's going to be a little bit better, but not much better. You can easily, you can easily export these models to QGeNIe. Let me take one of these and export it to QGeNIe. You essentially save it and can open it in QGeNIe. Here it is with full conditional probability tables that you can refine further. That's it. Thank you very much. You can play with the qualitative models in our online interactive online model repository, or contact us for any information. Thank you very, very much.